Welcome. Today we're going to continue our study of probability. Let's start by talking about joint distributions. So consider the two coin flip experiment where we define x to be the number of heads and y to be the number of tails in the experiment. So these are two random variables and we can consider their distributions. For example, x maps this outcome to 2. It maps this outcome and this outcome to 1, and it maps this outcome to 0. So it pushes forward each 1/4 probability mass to a location on the number line, and we obtain the distribution of x. With probability 1/4 here, 1/2 here, and 1/4 here. Y has the same distribution, but the masses come from different places. TT goes to 2, and HH goes to 0, and both of these outcomes go to 1. But clearly there's a relationship between x and y here that we're not capturing, namely that x plus y adds up to give 2. If x and y were independent, then that would be a different relationship than this one. So to capture this joint information about how x and y are related to one another, what we're going to do is map each outcome to the ordered pair x comma y in the plane. The resulting probability measure in the plane is called the joint distribution of x and y, and it tells us everything that we could want to know probabilistically about the way that the random variables x and y are related to one another. For example, in this picture we can tell that if x is equal to 1, then y has to be equal to 1 because the only probability mass along that vertical line is at this point. Likewise, if x is 2, then y has to be 0. If x and y were independent, but each had the same distribution that it has in this scenario, then the joint distribution would look quite different. All 9 pairs of elements from 0, 1, 2 would be possible. A second topic we're going to touch on today is variance. The variance of a random variable x is its average squared deviation from its mean. So we compute the mean of x, we subtract that from x, and we square the result and take the average. So in other words, if the distribution of x has masses, let's say here, here, and here, then perhaps the mean is somewhere like that. And then we measure these distances from the probability masses to the mean. We square them, and we average them according to the amount of probability mass at each location. And so basic properties of variance include that if you take the variance of a multiple of a random variable, that's the same as taking the variance of that random variable and then multiplying it by the square of that multiple. And that follows directly from linearity of expectation together with this formula, because the C you can pull it out of this inside expression and then it gets squared here, and then you can pull it outside of the outside expression. We also have the variance of x plus y is equal to the variance of x plus the variance of y if we know that x and y are independent. If x and y are not independent, this equality does not necessarily hold. So in problem 1, we're asked to find the mean and variance of an average of random variables. So to get a sense of what's going on, let's simulate some random variables. So here we're simulating 100 independent draws from the exponential distribution with parameter 1, which is just some probability distribution. So we get 100 values here, and you can see, some are quite small, others are larger. There's quite a bit of variance here. If we take the mean of such a sequence, and we do this repeatedly, then the answers are going to be closer together. So you can see it's frequently coming out to be quite close to 1 here. And if n is even larger, then that's going to be even more true. The answers are going to be very close to 1 quite reliably. So we're trying to understand that by calculating the mean and variance of this expression, which we'll do symbolically. So we start by taking the mean. This constant factor comes out by linearity of expectation, and also by linearity we can distribute the expectation across the sum. Now we're computing n instances of the expectation of a random variable with the same mean mu. So what we have here is mu plus mu plus mu n times, and that works out to mu. Similarly, when we compute the variance, the constant factor is going to come out, but this time it gets squared. So we have 1 over n squared, and then variance distributes across the plus sign when the random variables are independent. So this is going to be variance of x1 and so on up to variance of xn. So this is n copies of the same value sigma squared being added together. So that's 1 over n squared times n sigma, which is, n sigma squared, which is sigma squared over n. So what we see is that the variance goes down by a factor of 1 over n. So as n gets large, the variance is going to go to 0. And that's good news, because it means that if we have a random variable whose distribution may be difficult to understand directly, but which we can simulate, then we can simulate it many times and take an average, and that's going to be very close to the expectation of that random variable. This is called the law of large numbers. This second problem is another conditional probability problem. It's driving at the question of how we should update a probability measure based on partial information. For example, if we suppose that the prevalence of a disease in a population is 3%, then before you have any information, then your probability of having the disease would be 3%. There's an effective test for determining whether you have the disease, which is 98% effective in the sense that if you have the disease, your probability of testing positive is 98%. And if you don't have the disease, your probability of testing negative is 96%. So the question is, if you test positive for this disease twice, how sure are you that you have the disease? So we're going to visualize our probability space here as the leaves of a branching tree of possibilities. So at the start, we consider the possibility that you have the disease here, and then the possibility that you test positive or negative depending on that, and then similarly after you test the first time, whether you test positive or negative depending on that. And the problem statement asks us to assume that the two tests are conditionally independent given the disease condition, whether you have the disease or whether you don't. And the information that we're given about the outcome of this random experiment is that we end up in a condition where we tested positive twice, which means exactly that we're at one of these two states. So to figure out the probabilities that we're in each of the two states, we just need to figure out the proportion of probability mass within this set that's at each of the 2 points. And the point of laying out the diagram in a tree like this is it allows us to compute the probability of each element of omega by multiplying the conditional probabilities that appear in the path to that point. So for example, to get up to this top point, we multiply 0.03 by 0.98 by 0.98. And to get the probability of this point, we multiply 0.97 by 0.04 by 0.04. The proportion of probability mass at this outcome is 0.03 times 0.98 squared divided by that same value plus 0.97 times 0.04 squared. So in this case, getting the same result twice updates our probability from 3% to 95%. But that might be less than you would expect, given that you have two positive test results, each at 98% individually, but they're competing against this small 0.03 value. And this is how it works out. So notice here the conditional probability measure, one way to think about what it's doing is that it takes all the probability masses of all of these points, which are ruled out based on the final outcome, and it donates them to these two remaining points that are still considered possible. And it does so in a way that just keeps their proportion and grosses the total mass up to 1 inside the set that we're conditioning on. So now let's talk about conditional distributions and conditional expectation. So suppose that this diagram represents the joint distribution of x and y. It's uniformly distributed across these 14 points. And the question is, suppose you know that x is equal to some particular value, like let's say 3. That means that you know that one of those outcomes occurred. And given that you have no further information, you would assign each one a probability mass proportional to its original mass, so you'd get a probability mass of 1/4 at each of those 4 points. So we can say the conditional distribution of y, given that x is equal to 3, is uniform on the set 0, 1, 2, 3. And similarly, the conditional distribution of y, given that x is equal to some other value like 2, is going to be the uniform distribution on 0, 1, 2. Or on 4, it would be 0, 1, 2, 3, 4. And we could write all of those separate statements, but it would get quite tedious. So instead, we summarize like this. So this bottom statement is just a way to condense the top statement. The conditional distribution of y, given capital X, is the uniform distribution on 0, 1, 2 up to capital X. And all that means is that if we substitute any particular value, little x here for big X, in both locations, then we arrive at a correct statement. Now, we can also talk about the conditional expectation of y given x, which is just the expectation with respect to this distribution. And since the distribution of y given x does depend on x, in this case, the conditional expectation will as well. So for example, given that x is equal to 1, y is equal to 0 or 1 with equal probability. So on average, it's 1/2. So the conditional expectation given that capital X is equal to 1 is 1/2. Likewise, if x is equal to 2, then we have y being 0, 1, or 2 with equal probability, so the average is 1. And then similarly for x equals 3 and x equals 4. So we can summarize this state of affairs by saying the conditional expectation of y given x is equal to whatever the x value is divided by 2. And likewise, this is just an abbreviation for the conditional expectation of y, given that x is equal to 1, is 1/2, and similarly for 2, 3, and 4, so it's just a shorthand. We can apply the same idea in the case where the probability mass is smeared out, so it has to be represented by a density rather than a probability mass function. For example, consider this function 3/2 times x squared plus y squared on the unit square. If you integrate this function over this square, then you're going to get a value of 1, indicating that the total amount of probability is 1. So that checks out. And if we want to know the conditional distribution of y given a particular x value, what we're asking is just how is this mass laid out along a given vertical line. And so you can see on the left edge, the mass is more concentrated towards the top here by quite a bit. And on the right edge, it's still slightly more concentrated at the top because it's very dark up here and it's a little bit lighter down here. But it's more evenly spread out. So the conditional expectation is just going to be the expectation with respect to that measure. So on this left edge, it's going to start up pretty high because there's more mass near the top than near the bottom, and as we move to the right, it's going to shift down somewhat. We can work this out exactly using some formulas. And the basic idea is that if we start with the joint distribution, which is denoted f sub capital X comma capital Y, so this is all a label. There's just a name for one thing, which is the density describing where capital X comma capital Y is likely to fall. Then if we take a particular vertical line, we're just going to restrict this joint distribution to that vertical line, and that's going to tell us how the conditional mass is laid out along the line. So basically we want the conditional distribution to just be the joint distribution, except that when we integrate the joint distribution just along this line, we might not get 1, and the conditional probability distribution should add up to 1. So same thing in the discrete case. When we're excluding part of the domain, we need to adjust the amount of total probability mass we have on this new constrained subset of the domain so that it's equal to 1. So the conditional measure, which we're going to note f sub y given x, so again this is all just one name. It's the density for the conditional distribution of capital Y given capital X. And we're going to evaluate that at some particular point y. But it's common also to include in the notation that it depends on which little x we're looking at. So this is just notation for if we're at a particular vertical line, capital X, and we move up that line y units, and we're asking what's the density there for this conditional distribution. That's the quantity that's represented on the left-hand side. And the point is that we have to divide on the right-hand side by whatever it takes to make the right-hand side integrate to 1. Integrate y out and then divide by that. And now for sure when we integrate the right-hand side with respect to y from 0 to 1, the denominator doesn't depend on y, so it comes out, and the numerator integrates to the same thing as the denominator. So that's definitely going to be 1. And the thing is, this quantity on the bottom where you integrate out all the y values, so it's like you're taking all of the probability mass sitting along this line and you're sort of smashing it down to the x-axis. That's actually telling you just the distribution of x. And that's maybe a bit easier to think about in the discrete picture. Over here, if we wanted to know what's the probability that capital X is equal to, let's say, 4, it's going to be 5/14 because there are 5 1/14 likely outcomes corresponding to that result. So the probability that capital X is equal to 4 is 5/14. And likewise for the other values. So if we take all the probability mass and we smash it down to the x-axis, then we're getting the distribution of x. Likewise, if we wanted, we could sum up all the probability mass in the horizontal direction and get the distribution of y. So in the end, the formula has a very similar structure to the discrete case. The conditional density is the joint density divided by the density of the thing we're conditioning on. So that's very much analogous to how probability of A given B is equal to the probability of A and B divided by the probability of B. So the thing we're conditioning on ends up in the denominator. So let's do that symbolically here. So we find that the distribution of x is given by the density 3x squared plus 1 all over 2. And that makes sense. You can see there's more probability mass on the right edge than the left edge, but there's still a decent amount over here. And if we want to find the conditional expectation, we just need to integrate y times the conditional density from 0 to 1. And that's a bit untidy, so let's simplify it. We get 3/4 times 2x squared plus 1 over 3x squared plus 1. So that starts out when x equals 0 at 3/4, which is significantly closer to 1 than 0, and then it decreases as x goes from 0 to 1 to 9/16, so that's still above 1/2. So we can look at a graph of that, and it's going to look like this. So we just have some more examples of the same idea. So if x and y have joint PDF as shown in this figure, then it's telling you, for example, if you know that x is up here close to 1, then y is definitely not really small. There's no density down here. And then as you get larger, there's a larger chance that you'll see y there, and then in here there's the most density, and then it sort of falls off from there. And then there's another gap at the top where y is definitely not going to be. The conditional expectation just measures the middle of each of these vertical slice distributions. And you can see, based on the picture, it looks very symmetric around this middle ridge. So we get a conditional expectation that looks like that. So this last one is very similar. Let's just take a look and see that it matches our expectations.